So good morning. This is Leroy Wong at Burlington High School in Massachusetts, and I'm with the BHS Help Desk. And for Computer Science Education Week, we have Dr. Adam Lyon with the Fermilab, and he is a quantum computing researcher. So I know Adam personally through my wife, and actually Joe Perna, who's a student who I think is watching now in the other room. We had a conversation maybe about a month plus back about quantum computing, and then that's how I guess I thought about Dr. Lyon and thought about maybe having him as a speaker. So I guess you're our final speaker of the week, and we're so glad to have you with us. And I guess I'll go ahead and let you start with your presentation.
All right, great. Well, thank you so much for inviting me. And this is really interesting to be part of your Computer Science Education Week. Actually, there's people at Fermilab going to schools in the Chicago area doing similar things. So it's so thank you for making me a part of this big nationwide event. Yeah, so my name is Adam Lyon. I'm a scientist at Fermilab. This picture here is sort of a nice artist rendition of kind of our main building at Fermilab. If you ever come to the Chicago suburbs, to Batavia, definitely visit Fermilab. That's something you can do, and it's a really neat and unusual place to come. So when I was talking to Mr. Wong about what to talk about and what kind of questions do you all have, he actually sent me a list of questions, 23 of them, which is an awesome list of questions. I think this is from sort of a culmination of what some of you have watched on YouTube about quantum computing. And so I will try to address as many of these as I can. I kind of separated them into different categories. There's some questions just about me, how did I get to where I am, and what kinds of stuff have I done. I think some of you have watched some quantum computing YouTube videos, and they all kind of gloss over some of the concepts of quantum mechanics, which is the basis for quantum computing, especially superposition, which is really important to understand how quantum computing works. So I'll try to talk about that in detail. I'll talk a little more about how do quantum computers actually work, what they're good for. I won't talk about the quantum networking or quantum internet. That's a whole other thing, and that's actually very early days. It's all early days for all of this, but it's even super early days for that. And then at the end, I will try to talk about what if you want to get involved, and how would you do something like that. So I sort of already said all this, so maybe I'll just get right into the talk. So about me. So I went to undergraduate college in physics at North Carolina State University in Raleigh, which was close to where I lived. And when I went to school, to my first freshman year, I didn't really know what I wanted to do. I knew I wanted to do something in science or engineering. I wasn't sure what. And I liked physics in high school, despite not having a very good physics teacher. And so I sort of figured, well, I'll go into physics for the first year, and then I figure out what to do, right? There's time, and I could explore around to see what I wanted to do. And it turns out, the physics department was really nice. It's a small department. I had maybe 20 other students in my classes instead of hundreds, which the engineering classes had, and the professors were all really great, and so I stuck with it. It was really hard, of course. Physics is not an easy subject, but you stick with it. And then to decide what kind of physics to go into, that was really determined by a lab that we did when I was a junior, my junior year. So you take a lab class and you do kind of a lot of the foundational experiments in the history of physics. And one of them was building a cloud chamber. So I actually sort of reproduced that with my daughter Pauline a few years ago. And a cloud chamber is a way to actually see subatomic particles with your eyes. Subatomic particles like protons and neutrons and electrons, and even more exotic particles. These are things you were made of these things, but you can't see them with your eyes, right? But this is a way to do that, and so I'll just go through this really fast. This is kind of neat. So that basically you have this box, this black felt you saturate with isopropyl alcohol. I have a little movie here. Maybe I'll be able to stop it. Okay, so right? So this black thing is I don't know if you can't see my mouse. Let me see if I can. You might be able to see a little red dot. So if you can't see that, let me know. So anyway, this black thing is you squirt isopropyl alcohol on it. Don't drink isopropyl alcohol; it'll kill you. Not the kind of alcohol you want to drink. So you make this really full of alcohol, and then whoops, oh no, let me get that again. That's bad. Let's see. Okay, actually turning on the laser pointer makes this not work. There we go. Okay, so I won't do the laser pointer. So okay, so you saturate the alcohol, you put it in a base, you fill the base with chunks of dry ice that you can buy at some supermarkets. You make this thing really cold, and what happens is that a layer of saturated alcohol vapor is at the bottom of this thing, and this is what's called a thoriated welding rod that is slightly radioactive. You can buy these on Amazon. They're not dangerous, and this thing gives off subatomic particles. You can see these little wisps of clouds coming off of this thing. In fact, there's one up here. Towards the top, there's a big one that'll come, I think. And you can see these wisps of clouds. And what's actually happening is the subatomic particle, in this case, it's a helium nucleus, or alpha particle. They're being emitted from this rod. They ionize the air, so they strip electrons off of air. The atoms make up the air, and the globules of saturated alcohol like ions, and they glob onto it, and that forms this cloud. So you can actually see subatomic particles with a device like this, and this actually was very important for the history of particle physics. Several particles, like the anti-electron and muons, were actually discovered with devices like this. And I just thought this was the neatest thing I'd ever seen, and I decided to learn more about this and maybe make this my career in physics. So after I finished with a bachelor's in science and physics at North Carolina State University, I went to the University of Maryland, where I did my PhD. So that was 6 years, a long time. 1.5 years, the first 1.5 years were taking classes at Maryland, outside of Washington, D.C. And then for the remaining 4.5 years, I actually went to Fermilab. I lived here, and did my research on a big particle physics experiment. So this field is called experimental particle physics, or what we also call high energy physics, because we're colliding particles inside these huge devices, at nearly the speed of light. And so these are very high energy collisions. So that's why we're called high energy physicists. We work really hard, so we're tired all the time. So we don't necessarily have high energy, but the particles do. And I did a thesis which was searching for new particles called supersymmetric particles on this humongous experiment called the D0 experiment, which is one of two big experiments at Fermilab where we collided particles in the middle of this big device. In this lower left picture, you can sort of see a hint of what this thing looks like. I'll show you another picture in the next slide. What was really neat about this experience is that people from all over the world worked on this experiment. We had, actually, the numbers here are low. When I was on the experiment, which was sort of before this slide, a couple years before, we had about 600 people working on this experiment. Any given time, half of them were at the lab, and they were from all over the world. You can see kind of this group picture, which I'm in there somewhere. The flags from where all the institutions were from. So it was a really neat environment to meet people and just work with people from all over the place. This detector is huge, although nowadays, compared to the detectors in Europe at CERN, these are small. This thing was 5 stories tall, 5 million pounds, and basically this thing was used to discover the top quark, and I used it to look for new particles, which I didn't find because they weren't there. But that's a very difficult analysis to do, because you have to prove that if these particles did exist, you would have found them, right? So sometimes measuring 0 is harder than measuring, an actual value. So, and then I published a paper. This is the paper on the right from my thesis. And what's neat about high energy physics, we're very unusual in that everyone's name who's in the experiment goes on these papers. So every paper from D0 has about 500 names on it. My name is there. And you can't tell who's a professor, you can't tell who's a student. And it's just a really neat way to do it. It drives the journals crazy because they hate this. In fact, some experiments now have 3,000 people on them, and they don't even publish the author list anymore. They publish it once a year, and that's it. So, so I got my PhD in particle physics. You think with a PhD in, you could go off and get a real job, but in physics you can't. You have to do a postdoc, which is sort of a quasi job. You're basically doing all research, after your PhD. So that's 5 years, and I joined the University of Rochester, although I actually live in Ithaca, and that's where Mr. Wong's wife and my wife had met. At Cornell University, I was a postdoc there, because that's where the experiment was. And I got to work on a much smaller experiment, looking at different kinds of physics than Fermilab did. Still, so this accelerator, you can see it's sort of underground, carved into the side of a hill. There's actually a soccer field on top of it. This is a picture of the detector, much smaller. It was about 2 stories tall instead of 5 stories tall. But you can still see, pretty big. Here's a person actually working in the middle of the detector, putting something together. So after my postdoc, I then got a job as a scientist at Fermilab. Actually worked on D0 for quite a while, the experiment I was on for my thesis. But that ended in 2011. The experiment was done. And then you always have to be looking for the next thing to do. So then I joined this experiment called muon G-2, which I'm on today. And so this round thing that you see in this picture is a small ring. It's about 50 feet across, and we're looking for new particles in this thing. I won't explain it very much because this is a whole other talk. But this I'm actually a scientist working on this experiment. But this experiment, muon G-2, will only last another 4 or 5 years. We'll probably be done. We'll stop taking data in 2 or 3 years. It might take another year or 2 to finish the analysis, and then that's done. And I can't retire then, but I'm too young. And so I have to look for the next thing. And so I decided to sort of get my feet into quantum computing, as something to work on, more full time once this experiment is done. Actually, I'll make a note here. Someone asked if I need a security clearance to do quantum computing. Fermilab does no confidential work at all. So everything we do is open and is open to the open to the public in the sense that we don't have any secrets or confidential research. You can't necessarily walk into these things, but you can actually take tours. I give tours of D0. D0 is still there, even though we're not using it anymore. I've given tours of G-2. So again, if you're ever in the Chicago area, look me up and we'll do a tour. So it's pretty neat. Okay, so let's talk about quantum mechanics, because that's really the thing that drives quantum computing. And I don't think you all have had much, if any, quantum mechanics, so I'll try to sort of distill this into something that we can talk about, for the next half an hour or so, and hopefully you'll come away understanding some things. So, the world that we live in, or the world around us, is called the classical world. And so you'll hear me talk about classical computing and classical things. Those are the computers we have that are in front of you. That's the world that we live in. However, there are some parts of the world which are very weird, and that's the world of the very small. So here's this, this little diagram of a dewdrop and the atoms, the molecules inside, and then what's inside the atom. Quantum mechanics really is the theory that describes how atoms and how particles within atoms, how all that works. It was really developed in the early 1900s. So quantum is really for things that are very, very small. It's also for things that are very, very cold. So this picture on the right is a dilution refrigerator. There's actually a quantum computer at the very bottom of this thing. There's actually 2 of them. There's one behind the one in front. This can you see on the right says IBMQ on it that hangs from this truss. The very bottom is a quantum computer, and at the very bottom is among the coldest square meters in the entire universe. So wrap your head around that. We can actually make things, just barely above absolute zero. So this is measuring millikelvin. So I'm not sure if you know what that means, but it's really, really, really cold. It's colder than outer space. So it's among the coldest areas of the universe, and we can actually do this. And actually, if you have $500,000 burning a hole in your back pocket, you can just buy one of these. These are not hard. I mean, they were hard to develop and they're not easy to run, but you can just buy them off the shelf now. You can't go to Costco, of course, and get these, but you can buy them because we do that all the time. Okay, so that's sort of the realm of quantum mechanics. What I should point out is that quantum mechanics is used all around us, even though it's for things that are not in our not that we see all around us. There are things that are really, really small that we use, and one of those things are computer chips. So computer chips, this is a blown up picture of an Intel computer chip. There are 8 billion transistors in this thing, and transistors are kind of the basic building blocks of computers. And quantum mechanics governs how you build this thing and the limitations of building these things, how you can only make them so fast and so small. And so the material science and the way these things work are all based on quantum mechanics. You can't build an iPhone without understanding quantum mechanics. But the operation of this computer is not quantum mechanical. It's classical. And by that I mean they use bits, zeros and ones. We'll talk about that more in a little bit. So this is really what we call a classical digital machine. But what I wanted to point out was that quantum mechanics is all around us. It really just describes how our atoms work in the universe and ourselves, and how computers work. And just a neat tidbit. I saw a talk by someone from Intel who make these processors, and these transistors that are the building blocks or the pieces of these chips. Intel ships 100 quadrillion transistors a year, and transistors, he claimed, are the most ubiquitous man-made objects on Earth. So another interesting thing to wrap your head around. Okay, so let's talk about a little bit of stuff in quantum mechanics. So I think some of you heard of or watched videos about quantum computing, and they all talk about superposition, which is you have a system in some state. So here we have a coin, the quarter. The quarter can be either heads or tails. So you have two options for what the state is, heads or tails, or zeros or ones, or on or off. And in quantum, there's this phenomena where it can be in actually both of these states at the same time. And the way these videos ask you to think about this is like you're spinning the coin, or you're throwing it, it's flipping in the air. And so you don't know what state it's in. It hasn't landed into a state. And that's the analogy they use for this thing called superposition, that it's in more than one state in the same time. I actually don't like this analogy, because I think it makes more questions than it answers, because the quarter's in the state because it's moving, right? And that's not what's happening in quantum mechanics. So let's talk about what really happens in quantum mechanics. And I should point out that this is actually very mysterious in quantum mechanics. But quantum mechanics says this happens, but there's all sorts of interpretations as to what's really going on, and we don't know what the right answer is. But we actually use superposition. It works really well, and we can build things out of it, and test theories with it, or test experiments with it. And this is something that works extremely well, even though we don't necessarily quite understand what's really going on. But to get to this, we got to talk about waves. So you've probably maybe heard about the particle wave duality. Is light a particle? Is light a wave? Are electrons particles? Are electrons waves? We'll get into that a little bit. I don't want to talk about that too much, but that's sort of key to how quantum works. So you all know what waves are, I think. You drop a pebble in a pond, and you see on the left here, the crests and the troughs of the water caused by dropping that rock into the pond. And so waves, on the right, it shows what a wave is. It has a top part, it has a crest, it has a bottom part called a trough. It has other characteristics, and these things move, right? So the crest and its associated trough are moving in space. How the waves emanate from where you drop the rock in the pond. So I hope that's clear to everybody. And actually understanding waves was one of the foundations of quantum mechanics. It actually led sort of the early quantum scientists into our understanding of quantum mechanics today. And waves can do lots of interesting things, right? You can have two sources of waves. You can drop two rocks in the pond, and those waves will interact, right? So that's sort of depicted on the left. So where the crest from one wave and the crest from another wave, where they meet, they will add up and make a bigger crest. Where the troughs meet, they'll make a deeper trough. And if a crest meets a trough, they cancel each other out, right? So this is called interference. And this is actually, if you have noise canceling headphones, this actually is what's used to cancel the background noise in those headphones. You know, there's a fairly fast processor in the headphone that's listening to the background noise, and it's producing noise with the opposite wave to cancel the background noise wave. Right. So if you think about that, it's a pretty amazing thing that we can do. That's high-speed electronics that allow us to do that. Another thing we'll use is that, you know, if you put light through a prism, you know, white light from a light bulb or from the sun, you send that through, you know, a pyramidal piece of plastic, right? You get the rainbow coming out the other side, right? And that has to do with refraction and things like that. I won't talk about that, but just remember that this happens. That prisms are interesting. And so, in fact, here's a picture of one. So this is on the top left. Is, you know, you have a light bulb, and this is actually not a prism; it's a diffraction grating, but it works the same way. And you know, so you can view this rainbow. It separates the colors from the light bulb, and you see this rainbow on either side. So it turns out, if you put a gas in a tube like hydrogen, or something you see a lot, which is neon, right? Neon lights work this way. You put a gas in a tube or a bulb, and you put electricity through that tube, the gas will light up. And if you put that through a prism, then instead of seeing the rainbow, you see very specific lines of certain colors. And actually, there are other lines outside of the visible spectrum. So there are lots of lines that you can't see with your eye, but you can see with infrared detectors and ultraviolet detectors and other things. And so understanding where these lines come from and why they are where they are, that was really what drove the development of quantum mechanics, was understanding why hydrogen, if you send electricity through hydrogen and you look at it through a prism, look at its light through a prism, why do you see those lines where they are? That was really not understood at all until quantum mechanics. And one of the main ideas of quantum mechanics is that you have things at certain energies. So this picture is on the lower right, shows you kind of where electrons can be around an atom. So pretend it's a hydrogen atom, and instead of electrons, you know, being anywhere, you know, these are called energy levels. It takes energy to move electrons up to higher levels, and those are specific energies, and that's called quantized, and that's where quantum comes from. So you can't just have an electron at any old energy around the atom. It has to be at very specific energies. The lowest energy is called the ground state. That's where the electron will find itself if it doesn't really have any extra energy. But if you give it energy, it'll climb up to higher states, but only at certain energies. And then as it relaxes and goes back down, it'll give off energy at these certain energy levels, and that's what drives the spectra on the lower left. Right, so you're seeing the electrons falling down into lower energy levels, and they give off light at very certain energies. And understanding this was really at the time, the triumph of quantum mechanics. It turns out, you know, this picture here is very simplistic. If you have chemistry, you know that there's s orbitals and p orbitals and dumbbell shapes and all sorts of things. And this is a very simplistic picture, but for our purposes, this actually works quite well. Okay, so now let me talk about this very, very famous experiment. This will get us closer to quantum computing. I'll get there, I promise. This very famous experiment called the double slit experiment. And so the idea here is you have some sort of source, and here we'll call it a BB gun or something. And for this experiment, we'll just shoot BBs or rocks or something, and you shoot them at a wall, and there are two holes in the wall, and the particles can go through either hole, and then you have this backstop with a detector that it can say, where did most of the particles end up? And so the next image, thing marked B, where these two overlapping humps, it's sort of like, some of the particles go through the upper hole, some of the particles go through the lower hole. So if you have the detector right behind the hole, that's where, if you only had that hole, that's where the particles would end up. But you have two holes, and so some from the top can leak to the bottom. The trajectories can work out, they can bounce and things like that, and so you end up with this big overall hump of particles. Kind of the peak is at the middle. It's this broad hump, and the peak is at right in the middle of the wall. So in between the two slits in the wall. Okay, so that hopefully that makes sense, and that's something you can picture in your head. If not, you should ask me now, because we're going to continue onward. So one question. So that was for particles, BB guns, things like that. Well, what does water do, or what does light do? Water and light in this case are waves. And so say you have you're dropping rocks in a pond, and then you have a wall in the pond, and you have two slits in the wall. That actually generates sort of two sources of waves. Each slit generates its own wave that propagates forward. And as I mentioned earlier, those waves can interfere. And so where the crests meet and where the troughs meet, that's constructive interference. So where the crests meet, you have a higher crest, and where the troughs meet, you have a lower trough. And where a crest meets a trough, they cancel each other out. So instead of this big hump you see in the middle, which you do for BBs, you see this very fringe pattern. So the far right picture, don't worry about the eyes and stuff like that, and don't worry about the B picture. It's the C picture we're looking at. Instead of seeing this overall, wide distribution with the peak in the middle, you see these, the up and down, up and down, up and down, and so you'll see that as fringes in if you were to look at this in the detector, and we'll actually see that. And so the question is, what does an electron do? If you send electrons through this thing, is that going to behave like a particle? We think of electrons like particles, or will it behave like waves? And what turns out is really fascinating, and is very unusual. If you have an electron gun, which if you have an old TV sitting around, not a LCD TV, but an old cathode ray tube TV that actually has an electron gun in the back of the TV, shooting electrons at the TV screen. But if you take that gun out and you stick it, in this apparatus where you have a wall with two slits, and you have the detector, and you measure, where most of the electrons go on the backstop wall, you don't see the picture on the far right here, like BBs. You see the wave picture. And so this pictures on the right is what you actually see. The single slit pattern is what you would see if you had one slit or something that looks like this. But that's not what you see. You see this double slit pattern with all these fringes. That's where all the little, the black lines in and amongst the bright spots. Those are these fringes, and that's what you're sort of seeing in the distribution on the left. So this is really weird, right? So electrons are behaving as waves, not as particles. And this actually works not just for electrons, but for atoms and for molecules and for photons. And these are not electrons interfering with each other. You can actually send one electron at a time, and they will do this. In fact, we will see that right now. So here's an experiment that was done in the late 80s by Hitachi, which is a company in Japan. They actually built a double slit experiment, actually with a magnet, but that doesn't matter. So they have a source of electrons in this picture on the left. Electrons are coming out from the top. There's kind of a barrier in the middle, and there's magnets. So the electrons either go left or they go right. They can't go straight. And so that acts as the double slit, and then they have a detector. And so you can look at the detector and see where the electrons end up. And they're shooting one at a time. There's actually a bit of time in between each electron. So the electrons, can't see each other. There's only one at a time. And as this shows, and you start seeing dots appearing on the screen. It'll be done in another second, a couple seconds. And you see more and more dots. And he's actually this video is actually being sped up because it takes quite a long time to build up this picture. And what you start seeing are these fringe patterns. This in fact, you'll see it better. And so it's got half an hour to get this picture, and now it's very clear. You can see these fringes like you saw in the earlier picture. And this is shooting one electron at a time. So electrons are behaving as waves. right? So this is really weird because, which slit did the electron go through? And you can put a detector right behind the slit, and you can actually ask and answer, which slit did the electron go through. But when you do that, you ruin the picture from a double slit experiment. You get, in fact, the single slit pattern, not the double slit pattern. And so this is one of the main things of quantum mechanics, that doing a measurement changes the system, which is really weird. It's not it's not something that we think about in classical experiments, but in quantum experiments, the measurement itself is a part of the experiment, and you can ruin what's happening just by making a measurement. And so one way to think about it is asking which slit did the electron go through to make this pattern. One of the ways to think about that is the electron takes all the paths, like a wave. So it's really a superposition of all the paths, and these paths can interfere with each other, like the waves do, right? And so this outcome is given by superposition, and that all these paths are happening together, and where the electron will end up, what the probability is of where it will end up, is given by how these paths interfere, just like waves. So this is a very weird thing to think about, but it works. And this is what particles do in quantum mechanics. And so this is one of the mysteries of quantum mechanics. And there's all sorts of interpretations. There's some interpretations that say, thinking about what the electron does before it hits the back wall doesn't make any sense. There's other interpretations, like we talked about, that says, everything happens and things interfere. But we actually use that in quantum computing. So that's really how I'm going to talk about superposition. And so the way quantum mechanics works is that you have states. We talked about where electrons are around an atom, and these different energy states. So you have a ground state and you have excited states. I can kind of unroll the picture on the right and make it vertical. So you have a ground state and you have excited states. When we have sort of the basis of a quantum computer, in a regular computer, you have bits. In a quantum computer, you have qubits. And a bit has a 1 or a 0, or an on and on and off. And a qubit has a ground state, which we typically call 0, and an excited state, which we typically call 1. So the higher states in this case are not used. And that's instead of a classical bit, which we'll talk about here, we have things called qubits, ground states or excited states. But like we saw in the double slit experiment, these qubit states, the ground and the excited states, the electron can actually, or the device can actually be in both of these states in a superposition. And you can either think of it as that's something that's hard to think about and really can't ask the question as to what state is it in, or you can think about it as that it's in both states. Now we never see this because when we measure the qubit, it's either always 1. You measure a 1 or a 0. You measure the ground state or the excited state. You cannot measure anything in between. But before you measure it, it can be in this weird superposition of states, and we can use that to our advantage. In fact, the way we actually think about this is when we talk about, I see the Google Meet was a little bit behind there. Sorry about that. We actually talk about a wave function, hinting at the waveness of this thing. We had waves in the double slit experiment. We talk about the wave function, which describes the superposition, and there's two coefficients called alpha. I'll call them alpha and beta. They can be called anything, and these are called the amplitudes, and these lead to the probability of measuring the qubit in either 0 or 1, excited or ground or excited. And actually, it's the square of the amplitude that tells you the probability for finding the state, the qubit in the ground state or the excited state. So this is something that maybe should set off alarm bells in your head. When you measure, when you look in your computer memory and you read what's in the memory, the zeros and ones, there's no probability there, right? It's either a 0 or a 1. You're not going to have, unless something's broken, you're not going to have a chance of reading the wrong thing. But sometimes that can happen in quantum computing, and that has some consequences. So instead of thinking of quantum or qubits as zeros and ones, we can think of them as the superposition of zeros and ones. We can actually draw that as on this axis here. So the ground state is to the right, the excited state is up. And if you have, say, an arrow, you can be somewhere in between, the ground and the excited. And so imagine kind of setting up a qubit, putting it into a state. I'll explain that in a minute. And then measuring it. So you'll measure 0 or 1, and then repeating this lots and lots and lots and lots of times, right? So if you set up your qubit to be where the orange arrow is, where the coefficient for the excited state is 1, and the coefficient for the ground state is 0, then every time you measure it, every experiment, you'll get the excited state. And similarly for the green arrow, which is the bottom thing on this table over here. So you'll measure the ground state all the time. But if you set it up so that's in between, say you set up where this red arrow is, where the amplitudes, the coefficients are 1 over root 2, if you square that, you get a half, which means that half the time, so half of the experiments, you'll measure the qubit in the ground state, and the other half you'll measure it in the excited state, right? So that's how we see superposition. We can't see it as being in more than one state at once, but we see it as different probabilities for measuring, excited or ground. So hopefully that makes sense. Actually, I won't talk about this very much, but this picture is actually quite a bit more complicated. There's another dimension. There's something called a phase. So instead of a circle, we actually use a sphere. And this is called the block sphere. And you can have the states as shown as arrows in the block sphere. They can be very complicated. They can be complex numbers. I'm not sure if you've had complex math yet, but basically you need 2 numbers to describe each amplitude. And what's really interesting is that we can manipulate where these arrows are. We can set up an arrow in the sphere and we can move it around. So we can change the probabilities of how we'll measure things using what we call quantum gates. And so I'll explain that in a minute or two. So I talked about 1 qubit. You can have lots of qubits. And you can actually have qubits that kind of interact with each other. And that's called entanglement, which I won't talk about at all. It's a whole other talk, which is really interesting. Right now, there are machines that have 50 qubits. IBM and Google have quantum machines. I showed you a picture of an IBM machine in that can, the dilution refrigerator. They have chips that have about 50 qubits. That's kind of the state of the art. And when you do that, when you have multiple qubits, instead of the wave function describing 2 states, ground or excited for 1 qubit, you now have to describe all the combination of states for the multiple qubits. So for 2 qubits, shown in the middle here, you need 4 numbers, because 1 qubit can be ground, the other can be excited, they both can be ground. Sorry? Is there a question?
No, I'm sorry, I forgot to mute. Sorry about that.
Okay. So you need 4 numbers to describe two qubits. For 3 qubits, you need 8 numbers. And actually, you need 2 times that, because each amplitude requires 2 numbers to describe it. So if you have n qubits, like 50, you actually need 2 to the 51 numbers to describe that system. So a very small quantum system requires a huge amount of, let's say, memory on a classical computer. If you wanted to simulate this with a classical computer, to simulate 50 qubits, you would need 2 petabytes of regular computer memory to do that. And that's way more than your laptop. Your laptop, if you have a good laptop, maybe you have 32 gigabytes or 16 gigabytes. This is what, a million times that. So you really need a supercomputer to do this, to simulate these sorts of things. And 50 qubits is not very many. We're talking about needing millions of qubits to do certain problems. And so that's not something that you can really even think about on a regular computer. But that gives you a hint of if we have 1 million qubits, which can describe, which we would need, we can't even build a supercomputer that big to simulate it. It gives you some hint of maybe the computing power that could be in these quantum computers. So I'm not going to talk much about quantum algorithms. I'll give you a little example of one, but they all sort of follow a similar pattern, which is you have qubits, and you put the you have answers that could come out of a question you're trying to ask. I'll show you one in a second. And you kind of make a superposition of the qubits that represents all the answers, all the right answers and all the wrong answers. And so if you just measured that system now, you would randomly get a right answer or a wrong answer. So that doesn't help you at all. In fact, this is a sort of a common misconception that people talk about in YouTube videos, where they say the power of quantum computing is in this parallel. You have 50 qubits and you can interact with them all at the same time. It's actually not where the power is. The power is that we can manipulate these qubits to invoke interference. So we can try to create interference so that the states that lead to the wrong answers cancel each other out, like the crest meeting the trough in the double slit experiment. And the states where they lead to the right answer, like the crest and the crest, or the trough and the trough, those constructively interfere. And when you finally measure the system, you'll have a better probability of getting the right answer than the wrong answer. Now, there's still a probability of getting the wrong answer, which means that you have to do this experiment multiple times and do statistics to see which answer is more likely, and maybe that's the right answer. And we're also talking about doing things called error mitigation, which is actually having millions of qubits that you can compare to each other to try to figure out where these errors are. But this is a limitation of quantum computing, that you don't always get the right answer when you ask, when you look. So here's just an example. So this is something called Grover's search algorithm, which, if you look at quantum computing algorithms, you will notice that many of them are named after people, and that's because they're really complicated. So we give credit to the people who did the hard work in figuring them out. And so this is Grover's algorithm. So you can imagine you have boxes shown here. There's 8 of them, and say there's a prize in a box. So how do you find the prize? How many operations? How many times do you have to open a box to find the prize? So classically, at worst case, you have to open every box. Maybe the prize is in the last box that you look at. You get very unlucky. So that's at worst case 8 operations. Maybe you can say 7 operations, because maybe you can say, well, I've looked at 7. I know that I'm in there, so I know it has to be in the 8th. So you don't have to open it to say which one it is. So okay, 7 or 8 is the worst case. With quantum computing, here I just show for 3 boxes. So these are the combinations of ones and zeros of where is which box is right. For quantum computing, we can do this instead of 7 or 8 operations. We can do it in 3 operations, and that's really by having this graph on the bottom. Imagine all the bars are the same height, so every answer has the same probability, and then we do operations that make the right answer appear. The probability goes up for the right answer and goes down for all the others. It's actually quite complicated how that works. I don't have time to describe that, but that's really the idea of quantum computing. You're making the right answers, the probability for the right answers come up, and the probability for the wrong answers go down. And that's how this works. Okay, so I have another few minutes left, so let me try to quickly sort of talk about how do we make a quantum computer. It's actually really hard. Quantum computing is actually, as a field, has been around since the late 80s, but it's really only been in the last 5 years that we've been able to build quantum computers. And so that's why this field has just exploded within the past 5 or 6 years, because we can finally actually build these things. And so I won't talk about this too much, but basically there are structures, electrical structures, things called resonators. We have to build special ones that have to be superconducting, so they have to be kept very cold. We can make these oscillators, like springs or pendulums that go back and forth, that have certain energy levels and can behave like electrons, around an atom. They have different energy states, and you can give them energy, and they'll go up energy states, and they'll go down energy states kind of on their own. And you can manipulate these things. And we can actually couple these devices to radio waves. They're not actually radio waves. They're microwaves, sort of like what your microwave oven makes, but much more controlled. And not to heat things up, but to actually, we can rotate the quantum state around the Bloch sphere without looking at it. And again, this is something that's amazing that we can do. It's hard to describe how that works, but we can do this, and that's by coupling microwaves to this oscillator. It's sort of like taking a pendulum and moving it around by hand, right? You can take a pendulum and you can move it around by hand and have it swing in a different way, or have it you can speed it up and slow it down by hand. That's kind of what we're doing with these microwaves. This superconducting Josephson junction qubit is just one example of a qubit. There's other ways we can make qubits. We can take ions and trap them with lasers and then shine other lasers on them that behave sort of like the microwaves and manipulate the qubits that way. There's future technology that I will talk about that we hope will be used in the future. Here's actually a picture of what a superconducting qubit device looks like. This is on a chip. Not much bigger than a computer chip. And this is what sits at the bottom of that dilution refrigerator. And so where the arrow is coming from on the upper left, that's where the qubits actually are. So that's where these structures actually are. There's a picture of it. It doesn't really, you can't look at that and say, oh, that's a qubit. But that's what that is. And then there's these long kind of rectangles or snake-like things that kind of go back and forth. In the picture on the left, those are what are called resonators. Those are like antennas that feed the microwaves into the qubit, and also can kind of measure the qubit by listening for microwaves that the qubits are putting out. And that's how we measure we actually put a pulse in, and then the qubit will respond with a different microwave frequency, and that's how we will know if it's excited or ground. We can put these qubits together and actually have them talk to each other. You can arrange them in different ways. Qubits next to each other can do interesting things, and we use that in quantum computing algorithms. Here is what the quantum computers actually look like on the outside. You've seen the inside. Here's the outside. So here's this dilution refrigerator on the left, this big can. On the right is what's inside the can, and you see all these tons of wires. And this is only for 50 qubits. So imagine having 1,000,000 qubits, right? This technology will not work for 1,000,000 qubits. We cannot scale this up. And so one of the huge questions in quantum computing is, what is the technology that we can scale up to 1,000,000 qubits? This isn't it. So that's still what's being worked on. So I think one of the questions was, why this fancy chandelier type thing that's inside the dilution refrigerator? And the reason is because the chip itself is at the very bottom of this thing, and that's where the coldest area is, 10 millikelvin, among the coldest regions of the universe. And you can't just put wires in this thing, right? The wires will break. And they're different levels. The different platforms are at different temperatures, so it gets colder as you go down. And so, regular wires won't work, and so you have to use these, gold. I guess you would call them wires, but they're kind of rods, and they're very rigid, and these can withstand the extreme cold temperatures of getting these microwave signals in and out of the dilution refrigerator and down to the chip itself, where the qubit is, or the qubits are. Here's another really nice picture of what's inside the dilution refrigerator and all the electronics and the wires that are required. Fermilab is actually trying to build a quantum computer. We're trying to build special ones that don't do qubits, but do qudits with a D instead of a B. And the D signifies more than 2 levels. The B usually means binary. So qubits, excited and ground and excited. We're trying to build one that has many excited states, excited levels, and try to use that to our advantage. We actually build devices like these. These are called superconducting radio frequency cavities, and we build these for our accelerators to accelerate protons to nearly the speed of light for our particle physics experiments. It turns out this technology can be used to build a qubit. And so the real reason why Fermilab is involved in quantum computing, which is not really something you would associate with particle physics, but a lot of the technology that we develop has instant application for quantum computing. And we realized this and realized that we can really make an impact on the world of quantum computing by stuff we were doing already for particle physics. Let's see, I'm almost done. So just very quickly, there are limitations to quantum computing. You put the qubit in an excited state, it doesn't stay there for very long. The qubit wants to go down to the ground state, so it'll sit there in the excited state for maybe a millionth of a second, or many millionths of seconds, or in some devices a lot longer. But eventually it goes down to the ground state, and that ruins your experiment when that happens. Also, any exposure of the qubit to the outside world, which is any energy like heat that can come into the qubit, that will move that pointer around the block sphere, and it'll ruin your experiment. This is called dephasing, and that's the real reason why these superconducting qubits have to be in dilution refrigerators. They have to be so cold so that there's really no heat anywhere else coming in that would ruin the qubits and change the state, because we can't tell what that state is, right? We would measure it. We would measure something goofy. There's also something called fidelity. Sometimes you send a microwave pulse to a qubit and it doesn't always do what you want. We're learning how to manipulate these things better and better, but sometimes they don't do what you want. So error correction and fault tolerance is a huge part of quantum computing. So the type of problems that quantum computing wants to address are really ones that we think normal computers can't do. There's things called exponential type problems, where if you imagine, like I showed you the picture of how many numbers would it take to simulate 50 qubits. If you want, so as the number of qubits increases, the amount of memory you need goes up exponentially, until you can't build a supercomputer big enough to look at that. There are lots of problems that are like this. Simulating nature itself, you have hundreds of molecules or atoms in a drug, in a medicine, and you want to simulate that. You can't do that on a regular computer. So this is very interesting to drug companies and even perfume companies, to try to predict, what sort of pure perfume they have out of certain compounds. That's not something they can do computationally right now. But with a quantum computer, maybe because there's so much power in these qubits, as I showed you, comparing it to memory on a supercomputer, maybe there's something that can be done there. There's something called optimization problems. Here's a picture of your startup Boston. You want to deliver packages to all these towns. What is the optimal route that saves you the most gas? That's actually a very difficult problem. That's called the traveling salesman problem. And the more towns you want to visit, that problem blows up exponentially. And so you can't solve it anymore in a supercomputer. Imagine building an airplane, a 747 with millions of parts. How do you order, how do you put together the airplane in a way that minimizes the number of people you need or the number of tools? That's very similar to the traveling salesman problem. So it's these types of problems that are getting people's attention for the promise of quantum computing, and that's why airplane companies and car companies and drug companies are doing research in quantum computing, which is really interesting. You know about artificial intelligence. Quantum computing perhaps has the promise to really speed that up. And then I won't talk about it much more at all, but there's ways to break encryption with quantum computing. I should point out that none of this is real yet. These are all ideas. We have not. No one has written a quantum algorithm that we've actually run on a quantum computer that has beat a classical algorithm. Maybe you've heard about this quantum supremacy experiment that Google did, where they were able to show that an algorithm could beat a classical algorithm. Unfortunately, that was an algorithm that didn't do anything useful. I mean, it was cool for quantum computing, but not really for anything else. But we hope we're getting there. And so most people think that real applications are at least 10 years away, if not more. And an enormous amount of research and development needs to happen to get to that place. And so really, careers in quantum computing are just at the beginning. So this is an awesome time, if this field holds, if there's progress, constant progress, which we think there will be, this field is really going to explode. And so, if you wanted to go into this, becoming a physicist or an engineer or a computing expert or a data scientist or even a technician, these are all things that will have utility in quantum computing. If this is something you want to get interested in now or look into now, there are quantum computing camps actually for high school students. MIT has one. you gotta be a little careful that you understand you have enough math to really get something out of the camp. My daughter took one this summer, and she didn't quite have the math yet, and it was not so good. So just look into that. There's also high school curriculum. So actually Fermilab, a couple of Fermilab scientists published a quantum course for high school students. I can send this to Mr. Wong. There's a link here to a PDF document that has sort of that curriculum. That's something you can go through yourself. They explain the math, and so it's not so bad. And so, this really, this is something you're interested in. This is an excellent time to start exploring that. Okay, I see that I've gone over a little bit, so maybe we can ask, if you have time, 1 or 2 questions, and then we'll call it a day.
Okay, yeah, thank you, Dr. Lyon. That was pretty comprehensive. I was wondering, will we be able to get a copy of the presentation by any chance?
I'll be happy to send that to you. Yeah, no problem.
Thank you. That'd be awesome. Okay. So yeah, I'll open it up, and I know it's close to the end of class, and I know Dr. Lyon also has another meeting after this. So does anybody have a question? Like, are there 1 or 2 questions that anybody may have that you can?
Yeah, I had one.
Yeah, sure. Go ahead. All right.
So I showed up a bit late, so he might have said this, and I'm sorry about that. I just didn't find the link. But how many what is the amount of qubits they've been able to get in a working machine so far?
Right, that's a great question. So the state of the art is around 50. 53 is actually right now the largest. Google might have a 70 qubit device. They're hinting that they have one, but around under 100 now is the state of the art. So the next kind of big leap in quantum computing is getting past 100. That's what everyone is shooting for.
That's really impressive. Last I heard, it was at like 5 or something.
Right. So in the past 2-3 years, we've gone from 5 or 6 to over 50. So that kind of tells you how fast things are moving. Now, the technology for these qubits, like I mentioned, is not the technology that we can scale up to 1 million. So there's a lot of research in parallel to figure out what that technology would be, and that's proving to be very difficult. So there's a lot more work to be done there. But hopefully, there'll be 100 qubits or so in the next year. IBM has a roadmap for getting thousands of qubits, and we'll have to see. The technology keeps getting better. It's the big question is, will there be a wall that we can't cross? Right? Will we hit a point where there has to be a big breakthrough to get past it? And right now the problems tend to be engineering. Google tried to make a 72 qubit chip, and they couldn't make it work. It kept breaking. So and that was really based on the technology they were using to make the chip itself. But that's getting better. So we'll see. Thanks. That's a good question.
All right. So yeah, I know the bell's about to ring probably in a minute or two, but Dr. Lyon, if like any students had like burning follow-up questions, if I sent them to you,
Yes, I would be more than happy to answer questions.
Thank you. I really appreciate it. So thank you very much. It was great. And, I have so many more questions myself, but since I know you, hopefully I'll get some time to kind of...
Feel free. Yeah, definitely.
So anyway, that was Dr. Adam Lyon with Fermilab. This is Mr. Wong with the Burlington High School Help Desk. So thank you all for joining us. And, we really appreciate it. So Dr. Lyon, also happy Hanukkah. Please say hello to the family.
Thank you to your family, to you and your family too, and everyone else. Yeah.
Okay, and have a good rest of your day and a good weekend. Thank you.
Stay safe. Thanks.
Okay, take care. Bye.